All right, this discussion we're going to have today is on pressure. This is section 5.1 in your Zoom-Doll text. All right, this is the beginning of our discussion of gases. And as you are probably aware, or one of the things you've probably studied about gases, is that they will fill whatever container that they are put in. In other words, the volume of a gas expands to fill the volume of the container. Another thing that we'll talk about a little later in more detail is that gases will, on their own, mix completely with any other gas. And the focus of this discussion is the fact that gases exert pressure on their surroundings. Okay, the end of the chapter talks about kinetic molecular theory, but I would really like for you to think about these assumptions of the kinetic molecular theory. This is the theory that explains why gases behave the way that they do. And so there are four basic assumptions that we want to keep in mind as we go through these gas laws. And basically, when we get to the gas laws, what you want to think about is that our, quote, ideal gas is a gas where these assumptions of kinetic molecular theory apply. And so when these apply, that means the gas will behave in the way that the gas laws say that it will. All right, so the first thing to think about is that the volume of individual particles of the gas is assumed to be zero. Okay, and essentially what this means is that compared to the volume that the gas occupies, the volume of the individual molecules of the gas is considered to be negligible. The volume that they occupy is much, much larger than the volume of the individual molecules. Okay, the next thing talks about pressure, which is what this discussion is about, is that the collisions of the particles with the container walls, that's what causes pressure. And so the greater the frequency of these collisions with the container walls, the higher the pressure is. All right, and that's a very useful thing to think about, especially when you're answering some of the conceptual questions, is that just remember that pressure is nothing more than the frequency of the collisions of the particles with the container walls. Okay, another thing that they assume in kinetic molecular theory is that the particles exert no forces on each other. In other words, the path of an individual gas particle is not affected by it coming near a like-charged or an oppositely charged particle. That these types of positive, negative interactions do not affect gas particles. And then the last thing is that the average kinetic energy of the particles is proportional to the Kelvin temperature of the gas. We've talked a little bit about how the temperature of a substance is a measure of the average kinetic energy. And here we're being more specific in saying that this average kinetic energy is proportional to the Kelvin temperature of the gas. And this is important in that when you're using or performing calculations with gases, you have to always convert the temperature into Kelvin. Okay, so let's look at pressure. Pressure, as you're probably aware, is the force per unit area. Hence, a lot of the units of pressure that you're familiar with are probably directly look like a force per unit area. In other words, pounds per square inch would be a common example that is probably the pressure unit you're most familiar with. In SI units, the units of pressure would be newtons, which is a unit of force, per meter squared. And a newton per meter squared is defined as a Pascal, or PA. So this is one of our first units of pressure that we're going to deal with. Okay, we have a value that we refer to as standard pressure. And standard pressure is defined as 1 atmosphere. An atmosphere is another unit of pressure. Okay, and an atmosphere is equal to 101,325 pascals. Now we will, rather than using pascals, more often we tend to use kilopascals. So that would be 101.325 kilopascals. Okay, another set of units are millimeters of mercury in torr. These are equivalent units. In the next slide we'll see why that is. But 1 atmosphere is also equal to 760 millimeters of mercury, or 760 torr. Alright, so here is one of the original barometers. This was developed by a scientist named Torricelli. Okay, hence the unit torr. Right? And the way that they measured atmospheric pressure with this was basically you have the pressure of the atmosphere pushing down on the surface of the mercury. This forces mercury up into the tube, and the column of mercury will keep rising until the force due to gravity of this column of mercury is equivalent to the force or the pressure, force per unit area, of the atmosphere that's pushing the column upward. And then when this column stops rising, we take an actual distance measurement in millimeters of this column from the surface up to the height of the column, and that is our pressure measurement in millimeters of mercury. So that's where that unit comes from. Okay, here's another device that's used to measure pressure. This is called a manometer. Alright, and the way this works is you have a gas that you put into some kind of a bulb, like you've probably generated it and put it into this bulb, and we want to measure the pressure of the gas. Typically these bulbs are isolated by some kind of a little valve here, so we can isolate it from this little U-tube that has mercury in it. And initially the levels of the mercury would be even. And then when I open this valve here, the pressure of the gas will interact with the column of mercury. Now, if atmospheric pressure is greater than the pressure in the bulb, then the column of mercury will be pushed towards the bulb. All right? And you would measure the height from one end of the U-tube to the other, where the mercury column is. And if its atmospheric pressure is greater, then the pressure of your gas is going to be atmospheric pressure minus that height difference in the columns. Okay, similarly, over here we have our atmospheric pressure, and here the atmospheric pressure is lower than the pressure in the bulb. And so, as you can see, the pressure of the gas in the bulb pushed the mercury column the other direction. But again, we would take the height measurement between the two mercury levels, and if it shifts in that direction, indicating that the atmospheric pressure is less, then the pressure of the gas is just going to be the atmospheric pressure plus that height of the mercury column. Alright, so basically the types of calculation that you are going to be involved with pressure is just converting from one set of units to another, and we do that with a factor label. So to answer this question, I would have 3 atmospheres. To convert it to millimeters of mercury, I would use the relationship that 1 atmosphere is 760 millimeters of mercury. And so the answer to that would be 3 times 760 would be 2,280 millimeters of mercury. All right. In torr and millimeters of mercury are the same thing, so I would get 2,280 torr from that. And then to do kilopascals, 3 atmospheres. 1 atmosphere is 101.325 kilopascals. So 3 times 101.325. So I get 303.975, and that's in kilopascals. Okay, so that's how you would deal with the different units that we use to measure pressure.